Hello, everyone. Please type yes in the chat if you can hear me well. Right, perfect. We will start in 1 minute.
Good afternoon. Can you hear me?
Yes, we can hear you, Engineer.
Okay. So shall we start?
Okay, please share
Okay.
your screen and let me confirm it.
Okay. Can you see my screen now?
Yes, and your voice is there.
So good evening, everybody. Now we are going today to talk about the well test. What is the well test? And what is the pressure transient analysis in reservoir engineering? So first of all, we will define the well test. So any well test, whatever the type, and we are going to talk about the types later on in the slides. We perform a disturbance sent to reservoir by changing the rate, either production rate by stopping the production, or the well is shut in and we open it again, or the injection rate. Then the performance or response of these disturbances of the production are recorded by gauges, bottom hole pressures with time. So we have the bottom hole pressure that correspond to these changes, and we investigate or get more information about larger volume for reservoir, more than cores and logs. So basically, this is what we are going to do. Here we put a sensor in the well, and then we allow the well to be produced. So we have this production and we are recording through the sensor the pressure response in here. After that, we shut in the well while the sensor is here. So we have production to zero and we have the corresponding pressure in here. So what is the purpose or what we get from the well test is we can characterize the reservoir parameters like K, like permeability, scan, and so on. We can define the reservoir limits. We can see if we have boundaries, can identify the volume. We can see if we have a dual porosity system, and we are going to talk about the characteristics and properties of the dual porosity system. Also, we can have an estimation of average drainage area pressure and permeability and scan. Also, we can evaluate if we have a successful workover or stimulation like acid stimulation or frag that affected the skin, and we are going to talk about what is the skin. Also, we can see if we have a communication between wells, either in the same area or we are suspecting that we have a leaky fault between two different reservoirs. So through the well test or a type from the well test that we are going to talk about it, we will be able to evaluate the communication between these two wells. So, like I mentioned, this is typically the setup we use as a surface. I'm going to talk about some of you. I think they visited the field during training or so on. So we use a slack line to put a memory gauge to measure the bottom hole pressure and temperature into enable in the completion using a slack line tool. And as a surface, we have a test separator, a mobile test separator, in order to measure the fluid rates in terms of oil, water, and gas. After the production and shutting of the well, we have the disturbance, created the disturbance. We have the data from the memory gauge and send it for the interpretation, in addition to the surface rates when sample that we have. So we need to record the bottom hole pressure and the flow rate as a function of time. The well test requires sensors. The gauges at the wellhead are not accurate because we need to measure with a very accurate gauges up to zero point zero 0.05 or zero point zero 0.01 psi. That will make a change because we are going to analyze. And also we need a quick or fast readings. The recommended time or the number of readings per minute to be analyzed in the pressure transient analysis to be around 5 to 6 readings per minute and could be increased. So we need at least 5 or 6 pressure points per minute. So usually we set up the gauges to be a reading every 15 seconds or every 10 seconds because we need a high resolution pressure data. In addition to that, also we have the readings of the test separator. While production, we need to keep it as we can constant, stabilized with no changing, because it will affect the quality of the data. Also, we as a timing of the shutting or production periods, there is a rule of thumb that if we need to shut in the well for a week, as we will perform a test design, and I can talk about it later on how we design the test, but I don't think that we will have time for this. So there is a rule of thumb that we should shut in the well 3 times the duration of the production. So if we produce the well for 2 days, we will shut in for 6 days. Or we need to shut in the well to see a closer boundary. We know from the map that is a closer boundary, and I want to see it, and we calculated the distance, and it could be seen within 6 days of shutting. So we should produce the well for at least 2 days. Also, after retrieving the data, we need to perform the quality check about the water cut, the gas ratio should be constant. Also, the flowing tubing head pressure should be constant. We don't play in the shock or so. So what are the well test applications? In reservoir engineering, we have a lot of application. Is this zone economic? We have enough volume. We see boundaries economic to be produced. How large is the reservoir? What is the volume of the reservoir? What is the pressure currently? How can I describe this reservoir? How can I can get, if I have all the limits, I can get kind of estimation of the oil in place, can optimize the field development plan, can see the boundaries, also optimize the production. In terms of production engineering, is this well is damaged or is this well is tight, need type of stimulation like acid stimulation or hydraulic frac? Why is this well is not performing well as expected because of low permeability, because of damaged used skin? What is the optimum tubing size and artificial lift? Because we can generate the IBR from the pressure points that we are going to have from the well test. So, for example, if we have these two wells, the two wells are producing 100 barrel per day, and we need to know which well is worth money, assuming the same reserves. Meaning that I have the two wells at the same conditions, and I have money to be spent on only one well. So which one? I need to perform a well test in the two wells, and after performing the well test, it will identify the permeability and the damage. So in the first case, we have the permeability of 10 millidarcies, and second case, we have a permeability of 1 darcy. And assuming the same pressure. So we have the same production with the same pressure. So meaning that the higher permeability well is damaged. So I can treat this damage, and the well will be produced. If I treated this damage, this 100 barrel could be 1,000 barrel, for example. So from the well test data, I will evaluate the permeability, I will evaluate the skin, I will evaluate the pressure, I will know why this well is underperforming compared to other offset wells. Also, in terms of well test applications and benefits of the pressure transit analysis, that we can have a long radius of investigation. Like I mentioned, we can reach to some boundaries that can be kilometers away from this. So, if we checked radius of investigation of the other tools that available. So we have, for example, seismic that can reach to around kilometers, but seismic is kind of lines interpretation to the stratigraphic column of the layers. How deeper is this layer? Is this layer shallow? Then others there is anticline, syncline. I can have the structure map from the seismic. While of course, if we have it, I can have investigation to around half a meter, which is the size of the core, whole core itself. Logs also I can have few centimeters to less than meters. Then some logs that we can have, which give us the interpretation of the response of the rocks around the well. Also, the RFT and the MDT, I can have some samples, some pressure samples, but it's located around the well bore. While the well test, I can reach to the boundaries like I mentioned. Also, we have the tracers. Tracers, we use it in the water flooding in some application or steam flooding in some applications. Because if I have several injectors, I can give a chemical product to one of them. In case of breakthrough, in some ways, I can analyze the water that caused the breakthrough and identify the injector that caused this problem. Also, from the advantages, the interpretation softwares are available. Also, it's easy operations in terms of slackline and test package, and relatively very, very cheaper compared to other sources, like Course, for example, which is very expensive. Also, logs are very expensive. So at the well test, we need to collect the required information from the offset wells. If we have, we design the test, identify the shut-in period and the production period. We perform the test and get the analysis, perform the analysis, and then the recommendation action if we have as a field development or as a well restoration. So this is the required data to be collected. We need some information about the well bore. We need to have the well bore schematic, the current well bore schematic, the depth of the well, the perforation interval, the log information like the porosity and saturation, the drilling and perforation practices because it will give us a hint about the skin and damage if there is. Also the surface equipment like the test package and the Christmas tree or so connections. Also, we'll have a reservoir parameters like process saturation, the pressure, temperature, thickness, reservoir flow properties. Properties, porosity and saturation, we have it from the conventional logs. Reservoir pressure, we have it from the RFT or from the other analog wells. Temperature from logs also. Thickness, we have it at an NPA calculated from the CBI of the log, which is the processing of the triple comb, for example. Reservoir flow properties from the BVT report of this reservoir. If not, we can use an analog or offset PVT. Also, the geology is important. We need to have the map to see possible the outer boundaries, the boundary type, the distance, and also if we have a layering. If we have, for example, a reservoir that's composed from a good permeability zone and a tight permeability, this will affect the analysis of the well test. So we have basically two types of the well test, transient type and stabilized type. The main difference between them is the duration. From the transient type, we have a short duration. Only we need some reservoir characterization. We need to get some information about the permeability, the skin, and so on, and it's in the development wells. However, the stabilized, it requires long duration because we need to get a boundary detection, and some boundaries could be very way that even with stabilized production, we cannot see it. Usually, it's done in exploration wells to confirm the map or long-term production performance if we have an important, it's very important for us or critical to identify the boundaries for a field development. So the selection of the test and the test design should be depend on the objective that is required from the analysis. So the stabilized flow means that all the boundaries can be filled and we reach it to either constant pressure boundary, meaning that we find a feed into the reservoir, meaning that I have an aquifer in all directions, and the pressure will be constant. However, we can have a stabilized flow as a semi-steady state that all boundaries has been filled, but the reservoir acts like a tank. So we don't have a flow outer boundary. So we will have as this type kind of depletion after that. We will not see a charge from the aquifer because we don't have an aquifer. We just reach to the boundaries and the pressure will be stabilized. And if we open the production and close it again, we will see depletion because there is no charge. Also, there are two types of the well test. Well test that can be performed in single well test, like I explained before, a sensor installed in the well, and then we produce and shut in, or shut in and produce, or inject and stop, or a multi-well test that we put a gauge in a well and then we shut in or cause a disturbance in another well. And we will talk about the usage of the both of them. So we have here the types of the well test in a single well, which is drawdown, build up, injection, fall off, and step rate. What we can obtain from this, depending on the duration of the test, we can obtain permeability, skin, boundaries, reservoir shape, reservoir pressure, and also fracture pressure. I'm going to talk about each one of these five tests in the single well test in the next slide. So the first well, which is drawdown test. The well is static shut-in. We have zero production in here, and we have the original pressure. Then we open it for the production at a constant flow rate at the surface. So we have here as a constant flow rate. So it's very good for limit testing because the flow rate fluctuation is less. However, we have some disadvantages from them because it's very difficult to make the flow rate produces constant rate, especially for the low pressure wells. It will die. Also, if the well is recently drilled, it may not be static because it could have some flash production prior to the opening of the well. The most used one in terms of production, which is the build-up, which is also a combination between a drawdown and the build-up. So this is the most applied one. So we have the well flowing at the constant rate here, and then we shut in the well. So also it's very difficult to make the well flow at constant rate, but it's very important to keep it. And we, in this case, we can open the well for few days prior to the test till we have a stabilized flow rate. And this is the most used one. It's a combination of period of drawdown followed by period of build-up. After that, we have the injection test in which the well is static shut in, then we inject into the well. It's conceptually identical to the drawdown test. There is an advantage in this well. If we have in this way, if I have a well that I think it's very weak and I cannot produce it at a constant flow rate, I can inject because I can control the injection rates better than the production rates. So the injection tests are preferred in case of I have kind of depleted or weak or tight reservoirs that I think I will not be able to produce at stable conditions. That will affect the quality of the data that I'm going to be analyzed. Also, the fall-off test is very, very similar to the build-up test. Also, it's most used compared to the injection test. So in this case, the well injection and the injection, we are injecting water at the well at constant rates and we shut in the well. So we'll have a kind of fall-off of the pressure like in here. So constant flow rate is achieved easily because it's zero rate of injection. The last one is mainly related to gravel back illustration and so on, because we need to identify the fracture pressure. So we inject water, or most likely water, treated water, into the well at a series of different stabilized rates with a sequence of increasing. So we have an injection rate in here, and we record the bottom hole pressure. And also in here, we record the bottom hole pressure. And then we will find that by drawing, we will have different two trends, and the intersection point between the two trends represent the fracture pressure of the reservoir. Regarding the other type, which is the multi-well testing, we have two major types. One of them is the interference test. Why, when I use the interference test, if I suspect that I have a fault in here, for example, I have like this map, for example, and I have kind of fault in here, and I have well, it's called A, for example, in here, and another well is B in here. And I suspect that there is a communication between the two blocks, or the fault is not completely seen. So what I do, I insert a gauge in here on one of these two wells, and there is another well. And after that, I change the rate in the, I shut in this well, and then I change the rate in this well. And consequently, I see if there is communication between the two wells or not. Or vice versa. Yani I can either shut in the well or keep the other well producing, but I change only into the active well and see the correspond or the response on the pressure gauge. In this case, when he changed a little bit the rate, we have an increase of the pressure, indicating that this active well was drawing from this. So when I slow down the production, the pressure increasing here. So there is a communication. If there is no communication, it will continue like this. But it has a very advanced, it's very important tool to identify if the fault is sealing or not, or have communication between reservoirs or not, and it's very critical for the field development. However, it requires very sensitive pressure records and may take some long time, because the effect could be a kind of weak because of the distance between the two wells. The other procedure is the pulse test. I have the active well, also an observation well. So through the active well, I shut in the well, open it, shut in, open it through cycles, and I observe the bottom hole flowing pressure from the gauges. It corresponds to the shut in and the close. So I can confirm there is a communication. However, the analysis technique of this pulse test is very, very critical. So it's preferred, or it's more common to use the interference test compared to the pulse test. Any questions before I go to the other section? No questions? Regarding the dual process, we are going to talk about, I'm sorry, regarding the dual process, I'm going to talk about it in details in the next few slides. Okay. So now we are going to talk about some important terminology, which is the scanning. The scanning, the additional pressure drop change because of some heterogeneity happened near to or close to the wellbore. And also it reflects the connection between the reservoir itself and the wellbore itself. So it's a deviation or additional pressure drop from the ideal flow. For a damaged well, the additional drop is caused by reducing the permeability in the altered zone. So it's very important to identify the scan, because it will affect clearly the productivity, and it's very, very near to the perforations. What are the causes of skin? Some causes related to some drill fluid damage because of the mud filtrate invasion that may plug the pore spaces between the grains, causing permeability reduction. Also, if I am going to have an injection, either I have non-clean water that cause reactions with the fluids of the reservoir, causing a dirty water, or I injected incompatible water either with the fluids of the reservoir or with the formation. So before starting a water flood project, it's required to perform a compatibility test between the water or the injected water and also the reservoir fluids and formation. In addition to see the closely monitor the total dissolved parameters in the injected water to see if the water can be injected or cause damage. In some cases, we have a periodic acid stimulation jobs to the injectors to remove this injection effect. Also, in some cases, like I talked yesterday, if I have, for example, a retrograde gas reservoir and the pressure dropped to below the dew point pressure, we have some liquid phase or some condensate banking perform around the wellbore that will minimize the flow of the gas into the wellbore. Also, if I have reservoir, maybe the gas cause the same effect, but the gas effect is not like the condensate banking effect because the condensate is liquid and will affect the flow of the gas. Also, another definition, it's very important definition to be identified, which is the well bore storage. So if we open the master valve at the beginning of the well test, when we shut in the well, the fluid will rise to a level that will be equivalent to the pressure of the reservoir. And this is normal because it should be stabilized at the pressure of the reservoir. So when I open the well will produce from this column, from the well bore, and the formation will not share. The formation will start to share once I have produced some production, and it will increase gradually. So this is surface flow rate. Most at the beginning, most of the flow rate coming from the wellbore itself, from the fluid itself. Then the production from the reservoir will increase gradually till I can reach to that the sand phase or the production in front of perforation is similar to the surface perforation. This period represented by the wellbore storage, which is the effect of the production of the column of the fluid after, after opening the well after shutting period. In gas cases, it affects very much the analysis because of the compressibility of the gas. So when performing at well test for a gas well, especially with a high production rates like Mediterranean, for example, we have a shutting down all valves to shut in the well against the perforation itself to minimize the effect of existence of the gas into the wellbore and causing a huge wellbore storage time that could affect the analysis, especially in the case of the gas that is very compressible. So generally, what information that we can get from the well test, we can divide it into three stages. First stage is the early time, which is the near the wellbore, and here we can get the skin action. After that, the middle time region, we can have the K, the permeability and the pressure. After that, we have the late time that can reach it or not, depending on the boundaries on them and the location of the well compared to the structure. We can see the boundary effect. So what we have when we get this one, the rates and the pressure, we upload it into the software. We will have the pressure response and the derivative of the pressure response. We need to input into the software, like I mentioned, some more information about the well bore, completion itself, size of pipes, size of casing, and so on. the perforation interval, the PVD data of the fluid, the production rates, and the pressure data. After that, the software will generate these two curves, the pressure curve and the derivative of the pressure curve. At the old time, a lot of papers were published before the period when the invention of these softwares, type curves for different type curves that will go and match this data. And from this matching, we can obtain the information related to the well storage, skin, pressure, and permeability. But now the softwares has some analytical models and numerical models that can match most of the cases that we have seen during the well test. Now we are going to speak about these models. So in the real data that we have seen, we have shut-in period, for example, and then production period. We have this response, pressure constant, and then drop. However, in the software, we have a mathematical model that we input the data and we have the model output, and we need to calibrate the parameters in order to achieve or reach to the required parameters or the required results from the well test analysis, including the permeability, the scan, the pressure, and the well bore storage. Also, it's very important to highlight that we have several models, and it could be a lot of solutions that match and fit the data. So you should understand your reservoir. You should see the log. You should see the map, understand the behavior of the production in order to have the right mathematical model that represents actually the reservoir. For example, this is match it, same data you can see. Here, solution well nearing a seal fault. Here is a dual porosity system. Here is a dual porosity system also with a transient transition. Here is a dual permeability system. And we are going to discuss the differences between two of them. But for example, if I have a sandstone homogeneous reservoir, this couldn't be true because I don't have fractures. This most likely the true one. So I need to understand the reservoir, not choosing any random model and apply regression techniques to get the match. I need to understand actually what is the reservoir to choose the best or the most best fit model for solution. The importance of the productivity of the well test, we can identify the productivity like mentioned. We can construct even the IBR curves. For oil, we can have the productivity index, and for gas, we can have the well derivability equation, which includes the N and C. Also, from the drawdown flow periods, like we said that we can have the early transient values K and S. We can have also, if we have ratio to the middle of reservoir, we can get the mobility and the skin. And if we reach to the boundaries, we can have the variability. In case of the build-up periods, we can have the average permeability of the reservoir and also the average reservoir pressure. So from the early time region, we can have the well storage if we have fracture, if we have turbulence flow, and if we have skin. In the middle time region, we can see have the permeability and the pressure. So the permeability and the pressure, also the type of reservoir, if it's homogeneous, the dual porosity, dual permeability, composite reservoir, or multi-layer reservoir. And the late time, we can have the boundaries, single boundary or multiple boundary, a closed system, constant pressure or not. And we are going to talk in details about each type of these models. We'll talk first about the early time models, then the middle time models, then the late time models. Before starting, any questions? What happens in unconventional reservoir? Regarding the unconventional reservoirs or very tight reservoirs, we are using another technique which is called rate transient analysis, which allows to produce the well. We have gauges either downhole or either at the wellhead and then convert it to be downhole. From the rate transient analysis, they can obtain a lot of information about unconventional. It's very common used in unconventional reservoirs, for example, shale oils in USA or so. So they use a rate transient analysis, not a pressure transient analysis, which is another technique that allow to record the pressure. And we don't need a huge time resolution. It can be a reading per day in order to obtain the volume and assess the reservoir properties. Regarding the well test, so we can assume that if we have an oil reservoir, we can assume that we have a constant well bore storage. If we have a gas reservoir, like I mentioned, it's preferred to have a downhole shuttle tools to govern the production and to minimize the time of the well bore storage. So generally what we do, we install the gauges in here, we open the well for drawdown, then this is a period of well bore storage, then we have the same rates for sand phase and surface. We stabilize the production at the same time, then we shut in the well and we have the build-up period. When we enter the data into the software and we have this is the pressure and the derivative of the pressure. So if we have a huge Wilbur storage, we can see here it's high. And it will have at a log plot, it will have a unit slope. So here we have a high Wilbur storage. However, here we have a low Wilbur storage. So in case of log response to identify the storage, we will have at the log response a unit slope of 1 until we pass the time of the pressure disturbance from the wellbore storage. In case of the multi-phase flow, we have an oil with high reservoir ratio. We can have a changing wellbore storage option, and it's very difficult to have it. It's applicable in software, but it's very difficult to the match. Of course, like I mentioned, the magnitude value of the wellbore storage depending on the type of completion, if we have a surface or downhole shuttle. Also, if I have fracture, there are two models for the fractures. If I need to evaluate post a hydraulic fracture job, so if I have fracture, there are two types of fracture that can be characterized. The first one is infinite conductive fracture, and it's assumed that there is no delta B losses along the fracture length. So the flow lines pattern go orthogonal to the fracture, and the transient pressure have a linear flow into the fracture. However, in infinite case, it's assumed that there is no delta B losses. Like I mentioned, this is a mathematical model that could not fit 100%, could fit 90% of your case, but it's the most realistic case or the most matching case to your case. So it could be the delta B is very, very low. So we can see the the infinite conductivity fracture. In this case, we can characterize it that we will have a half slope at the beginning after the Wilbur storage, or even could be masked by the Wilbur storage. So it's important to minimize the time of the Wilbur storage in order to see the very near action. So if we have a half slope at the early time, linear flow, this is infinite conductivity fraction. In case of finite conductivity, it's the same. Also, the flow line pattern is orthogonal to the fractures, but we have transient pressure is bilinear flow. So bilinear flow indicates that we having a delta B losses along the fracture lengths. And it could be having like this. Bilinear flow is quarter slope, however, the linear flow is a half slope. And we can see a combination between them. Finite conductivity can be composed both of them together. Bilinear flow first and then linear flow second. This is quarter slope and this is half slope. Also, if we have a partial penetrating wells, so the perforated interval is very small compared to the total thickness of reservoir. So we can see some flow coming from up and down to the perforation. So we can have spherical or hemispherical flow, depending on the position of the opened interval with respect to the total thickness. So in case of, for example, spherical flow, we can see that we are having some flow in here, which can be represented by this flowing period. And after that, we will have the flow from up and down going to the perforation. And it could be characterized by spherical flow, which have a negative half slope. After that, we are going to see the response of the reservoir away from the wellbore, so it will be continuous flow like this. So we'll reach to the AIRF or radial acting flow. Also, there is a very important impact of the permeability on the spherical flow. So if we have a decrease in the permeability, we will see the curves or the derivative curves are going to up. Now we are going to talk about the mid-time region mathematical, or mid-time region models. Before this, any questions related to the early time models? Any questions? Okay, so we are going now to talk about the mid or uh, the middle time models. So the first one is the homogeneous reservoir, and the assumptions are that the reservoir is homogeneous, isotropic, and has a constant thickness. So in this case, we will have at the log-log plot the radial acting finite flow. It will be slope of zero like this. Also, we will have it on the Horner plot. It will be a slope with a straight line with an M. So we will have, after the influences of the Wilbur storage that will have a slope of n, then we will have infinite active radial flow, which can be known as IARF. So we will have this either this line on the log-log plot or this straight line slope on the Horner plot. So as a log-log response, it will be a horizontal line, and its parameters depends on the permeability and the skin, of course. And with the specialized plot, it will, or the Horner plot will have a straight line with a defined slope called M. If you go back to your college note, you will see that M can be used to calculate the permeability and then a function of skin. The dual porosity system or the dual permeability system, uh, that we are, it's assumed that we are having a matrix and then we have a fissure, either vugs or fractures, and then the matrix is feeding to the fracture, and the fracture is going to the, this is the lower porosity. In case of the dual permeability, both of them, the matrix and the fractures, are both feeding into the well. So the Fisher system is assumed to be uniformly distributed throughout the reservoir, which is not that right, but it's kind of estimation about how much the Fishers compare to the matrix. Also, in case of dual porosity, it assumes that the matrix is not producing directly to the wellbore, but only to the fractures. The dual permeability system, and we are going to talk about the differences between them, is assumed that both of them, matrix and fracture, are producing into the wellbore. Also, it assumes that the only Fisher system provides the total mobility, but the matrix supply most of the storage capacity, meaning that the matrix provides feed into the fractures, and the fractures only feeds the well group. We have some important definition that we need to identify: the total porosity, that is the porosity of the both of them, the fraction of the matrix, also the total K of H, which is the Fisher system only in case of the dual porosity, the storativity ratio, define the contribution of the Fisher system to the total system, meaning that how much of the fluid is stored into the fracture compared to the matrix. Also, the interporosity flow coefficient defines the ability of how much feed from the matrix is able to flow into the fissures, either arcs or fractures. However, also alpha is related to the geometry of the fissure itself. So if we checked the effect of them, first of all, we are going to talk about the sorority ratio, which is omega, which gives an indication about the fraction of the hydrocarbon or the fluid stored in the fissures compared to the matrix, and is function of the porosity, the compressibility, and the thickness of the both of them. And this is the effect of increasing the omega. You can see the hump will be increased. Also, the interporosity flow coefficient represents the permeability contrast between either the matrix and the fractures. Also, the alpha, the shear factor, and depends on the matrix geometry. This is the effect of the increasement, or sorry, this is the decrease of the. This is not the effect of the increase of the lambda, or the interporosity effect. This is the effect of decreasing. It will move to the right. Now we are going to see the differences between the dual porosity and the dual permeability system. In case of dual porosity, only the porosity one, which is the porosity of the matrix, is extended the well. However, sorry, this is porosity one is the porosity of the fracture. However, the porosity two acts only like a source that feed only the fracture. The double permeability, so both of them are connected to the well bore, so the both of them, either the fracture or the fluid, can go and feed the well. Another model that can be defined is called the radial composite model, and we called it a key master model because it can match any data that you have, any data literally. So if we have a well at the center of the circle, homogeneous zone of of radius of r, communicating with another zone, so we can have assume that this zone have a permeability different to this zone. So we can have two layers out of each other that have different properties, or different flow properties, or different reservoir properties. Also, it's assumed that there is no pressure loss according at the radial interface. So we need to some parameters to define the change that, or the difference between the two permeabilities between the outer zone and the inner zone. This is called the mobility ratio, which is a relation between the permeability and the viscosity of the first zone and second zone. Also, the storativity ratio, which is the relation between the porosity or the total stored volume in the zone, inner zone, and the outer zone. If we checked the performance of the two wells, here is some different mobility and storativity ratios. So here, if we have a homogeneous reservoir, we'll have a horizontal line. If we have an increase of the mobility and storativity, it will be going up, and we'll see another IARF. And if we have a lower zone, then it will go down, and we'll have also another IARF, or infinite acting radial flow. In case of linear composition, it is almost the same. Also, we have two zones around the wellbore. One of them, or one direction, have a different permeability compared to the other. And also, there is no pressure loss around this interface. So can be also calculated through the two same two parameters, which is the mobility ratio and the storativity ratio. And similarly, it will be the same. If we have a higher mobility and higher selectivity ratio, it will go up, and if we have a lower, it will go down. Now we are going to talk about the late time region models. Any questions in the middle time region models? Okay. So in the other late time region models, we have closed system or composite boundaries, which we have four boundaries that can be filled in here. In this case, we have two cases. Either we have no flow boundaries, meaning that we reach it to the boundary and it's not feeding anymore from other side. So the closed system and we don't have any boundary. So how we can know it? We will have the two pressure. Like I mentioned to you, we will produce the well for a period, then shut it. So we'll have this response in pressure like this or like this. So after the analyzing, we can analyze the build-up period and the drawdown period. So the build-up period will give us this drop. However, in the drawdown curve, it will have an increase. So we can identify that we reach to the four boundaries. So if closed system is defined, then we we will reach first to the infinite acting reservoirs. And if we have, like we mentioned, if we have a constant or closed system without any constant pressure, then we will have a drop into the reservoir in the build-up curve after reaching, and we will see an increase in the drawdown. In case of circle reservoir, we can have also closed system as a circle. It will be the same. We will reach to the infinite acting radial flow. After that, in the drawdown, it will have an increase in the drawdown, and then pop build up. It will drop. Also, what if we have a single boundary or a single fault? It can be identified like this. It will be have a small infinite acting radial, then it will increase a little bit. And if we have a double on the honorable double slope of the slope of the infinite acting radial flow, it indicates a single boundary or a fault boundary. In case we have a partial communicating boundary, we'll have some kind of increase and then it will come back again to the infinite line. However, if I have a ceiling fault, it will be up compared to this well, compared to this performance. In case we have an intersecting boundary or a wedge, we have here two cases. The first well is centered and the other well is off-centered. And both of them that we will find that we will have a kind of steps that we are having. So this is the first case we will have a step and it will be uniform. The second one is the upper one and it will be two steps to reaching to this one. If we have a channel of boundary, also centered of or off-centered, can be characterized on both of them with a slope at the lead boundary with slope of a half. And if its well is off-centered, we can see this hump compared to this one. Of course, the geological maps will be helpful a lot in understanding the reservoir model that we are having because it's very important to understand the reservoir not only to fit a model that mathematical model that can be fit into any data. In this case, we are going also to see this is a closed system and also this is the closed system. In case we have A constant boundary. I will open the slide to show it to you. So in this case, if I have a constant pressure, then I will have a pressure drop here. And if I have a flow from one reservoir, it will or one boundary only, and the other boundaries are no flow, it will affect and mask the other effect of the other ones. Thank you very much for your listening. We talked today about the importance of the well test, how the well test is performed, what is the data required, what we can get from the well test. Also, I talked quickly about some information or some guidance about the models, early time models, in order to obtain the well pro storage, the scan, also the middle time models like radial composite, like homogeneous, like dual porosity, in order to obtain the other reservoir properties in terms of permeability and the pressure, and also the late time models, which is the boundaries. Of course, this is a big topic to be discussed in 1 hour or one session, but I think gave a brief, tried to give a brief about all of these topics. Thank you very much. And now, if you have any questions, please. Any questions?
I think there is no question here, Engineer Ahmed.
Okay. Okay. So if you
Okay, thank you, Engineer Ahmed.
thank you very much.
Thank you for attending this session. Thank you all.